we will look at a concept called Reynolds analogy, which is an important concept in boundary layers where you have a temperature variation between the fluid and the solid. So Reynolds was very interested in looking at the heat transfer either from the fluid to the solid or from the solid to the fluid. For example, if you have a very hot radiator plate, a cold air flowing over that, heat will be transferred from the hot plate to the cold air. On the other hand, in the case of a turbine blade, for example, the external flow is very hot, the blade is colder, so the heat is transferred from the hot air into the turbine blade surface. So in all these things, we have some heat transfer taking place. So how can we measure the heat transfer rate? How does it correspond to things like skin friction on the boundary layer? So this is what Reynolds was asking about. This Reynolds is the same one we have seen in many other places. We have seen a Reynolds number. We have seen the Reynolds experiment, a transition of flow in a pipe from laminar flow to turbulent flow. And this is the same Reynolds that we are looking at here. So we start with the energy equation, which was formally derived in a previous module. So we're just going to write it down. I apologize for the handwritten notes. Hopefully it's visible to you, clear to you. If you look at the energy equation in 2 dimensions for steady flows, it had the following form. Let's just walk through the various terms. This is just on the left side of the energy equation. To look at the full energy equation, we should go to the module on in our course notes. If you go to the energy equation in viscous flow, probably the last slide, let's see. Okay, this is the energy equation that is developed in our class notes. Here this E is the total energy per unit mass. Total energy means it's got an internal energy, which is a specific energy, specific internal energy, but it also has got a kinetic energy. So the total energy is defined somewhere way up here from the energy equation as specific internal energy plus the kinetic energy. So the energy equation has got this long form. We have a separate video on it where we derived it step by step, and it's recorded, available to you on Canvas. So it looks like this. Now we are going to look at the left-hand side and then the right-hand side in our PowerPoint slides, in our PDF, handwritten PDF notes. Okay. So first we are going to look at the left-hand side. We are looking at the steady flow. Okay. So returning back to our PDF file, this is what we have on the left side. Rho U times the big capital E is internal total energy, which is shown in here. But notice that the total energy is CV times T plus 1/2 of velocity squared. Now, if you write P as rho RT, then you can pick up an R times T from this P with the U left over. So rho U times CV times T plus U squared plus B squared over 2 plus RT. CV plus R is CP. Therefore, you're going to get CP times T. This is the enthalpy. This is the kinetic energy. This is same way in the y direction. So again, going back to our PDF file, we have grouped all these terms together as rho U times, this is unsteady term, so we neglect it because it's a steady flow. Rho U times Cp times T, which is the enthalpy plus kinetic energy per unit mass. So that's same way rho V times Cp times T plus kinetic energy which is again enthalpy plus kinetic energy. So that's on the left hand side. Now if you rearrange it, you get rho u. You could think of this as a P times Q. Then it is P times dq dx plus Q times dp dx. Same way, if you think of this as a P and Q, P times dq dy plus Q times dp dy. Now when you look at it, these two terms together, in steady compressible flow, they go to 0. Therefore, our energy equation, the left side of the equation, just contains only these two terms. On the right hand side, you have the conduction term and you have the viscous work term. Again, we had developed it some time ago in the previous video, conduction term and the viscous work term. Now the viscous work term is explicitly written like this. Now we are going to invoke the boundary layer approximation. Remember, we are interested in the heat transfer from the fluid to the solid at the interface between the fluid and the solid. So either the fluid is hot compared to the solid or vice versa, it doesn't matter. So, but we do know that this layer is going to be very thin, just like the mixing layer for the momentum thickness boundary layer is going to be very thin. So we could invoke boundary layer assumptions. We know, for example, the vertical component of velocity as a fraction of the edge velocity is going to be of the order of delta over L, where delta is the boundary layer thickness and L is the distance of the airfoil or a flat plate. So because the V is so small, its squared can be neglected. So wherever I see V squared over 2, I'm going to neglect it. All right. Compared to U squared over 2 and U squared over 2. We can also neglect the streamwise conduction term, keep the normal direction conduction term. Just like in the boundary layer theory, we dropped the viscous terms in the x direction. We kept the viscous terms because they are changing very rapidly in the y direction, normal direction across the boundary layer. So we are going to neglect this term. Same way, in the viscous work, we are going to neglect the streamwise terms. We are going to keep the cross term. So once we do that, boundary layer invoked, we have neglected the streamwise conductivity, streamwise viscous work, then we get a somewhat simplified form of the equation that looks like this. Now compare this to the U momentum equation. This is the U momentum equation that we developed a long time ago when we talked about the laminar boundary layer. So we see that there are some things similar. I have a rho U, derivative of something, rho V, derivative of something, first derivative, K, here I have viscosity, derivative of temperature, derivative of velocity, and then derivative of, here I have a viscous work term, extra term, I have nothing out here. So let's multiply the second equation by U all across. Then take the U inside the derivative. For example, U times du dx will be dx of U squared over 2. U times du dy will be du dy over U squared over 2. Then you'll have a U times dp dx from here. Then we take this U inside here. You'll have a U times mu times du dy. Now, you have, this is a product rule. So this is like a P times Q. So you'll get U times dq dy minus Q times dp dy. So that would be this term here. So this is what we get. So now we see some terms here which look very much like the terms here, very much like these terms here. So from 1, let's subtract 3. Subtract 3 from 1. then we get an expression that looks like this. Now for a flat plate, we know that there is no acceleration or deceleration of the potential flow, edge flow. So the dp dx is 0. So Reynolds was primarily looking at a flat plate because that's the easiest configuration to look at. So he said, I'm going to reduce my dp dx equal to 0. Then this term is called a viscous work term, and that work term becomes very strong in high-speed flow, supersonic flow, hypersonic flow. Because when one layer of fluid is rubbing against another layer, heat is generated, kinetic energy is destroyed, it is getting converted into heat. So in high-speed flow, high Mach number flow, this is very important, but it's negligible at low-speed flow, subsonic Mach number. Therefore, Reynolds neglected this last term in equation 4. He neglected this last term on the left side also. Therefore, for a flat plate at low Mach number, equation 4 simplified to something like this. When you compare this with the momentum equation, we see they look very similar. This is the Reynolds analogy. They are analogous to each other. Both of them look very similar, except this has got a CPK over CP. This has got a mu here. Now, if you define a number called Prandtl number, mu Cp over K, Prandtl finally got a number after his name. We have Reynolds number, we have Mach number, we have all kind of numbers in fluid dynamics, but Prandtl finally got a number for him, named after him. This is this number. Now it turns out that for air in laminar flow, Prandtl number is of the order of 0.72. In turbulent flow, this viscosity will include not only the molecular mixing but also eddy mixing. Remember the eddy viscosity we used to talk about? So the Prandtl number is about 0.8. So in either case, it's close to 1. So if you assume Prandtl number to be 1, then K over Cp will be equal to mu. Okay, if this is 1, K over Cp equal to mu. Therefore, equation 7 results, which looks very much like equation 5. So again, momentum equation is analogous to the temperature equation for a flat plate, subsonic boundary layer. So think of it as a radiator fin on your car engine is sticking out, air is flowing over it, trying to cool it. So there's heat transfer taking place from the air into the fin surface. So the air forms a thin layer of boundary layer on the fin. So the boundary layer has got a momentum thickness, it's got a velocity boundary layer, but it also has got a thermal boundary layer. So what Reynolds is saying is the distribution of the velocity in that boundary layer behaves very similar to the distribution of the temperature in that boundary layer. Based on that, we can write a general form of an equation for the temperature as AU over B. So if you plug this solution in here, you could verify for yourself that B will drop out because it's a constant. Wherever it shows up temperature, it will drop out. A is a constant, so it will come out of everywhere. Then T will be replaced by U, T will be replaced by U, T will be replaced by U. Therefore, equation 7 will simply become equation 5. Therefore, Reynolds postulated that temperature behaves like velocity. Temperature profile is going to look exactly like the velocity profile for a flat plate if Prandtl number is 1. Granted, this is an approximation, but he was just trying to get some physical feel for what's going on. That means that temperature derivative is going to look like the derivative of the velocity. At the wall, if you multiply this by K dt dy is going to be A times K du dy. Remember, Reynolds Prandtl number, mu, Cp, and K are related to each other. So you can replace the K by mu Cp over PR. So you could write it as mu Cp over PR. Now mu times du dy is the shear stress at the wall, Stokes relationship, stresses at the wall. This is the heat transfer rate according to Fourier at the wall. So the heat transfer rate at the solid wall is proportional to the shear stress at the solid wall. Therefore, the Reynolds analogy simply says that the heat transfer rate is analogous to the shear stress at the wall. This is it. So this is Reynolds analogy. This is a very important physical concept. So this could be derived with very simple arguments, starting with the energy equation that we had previously developed.